right? Uh, um, and along with that, next came data science and machine learning, because when we talked about analyzing the data and coming up with a good way to use the data for business purposes and for fulfilling the customer's need, there are only limited ways that it can be done, right? Um, what is the best thing that people were able to come up with? They were able to look at the data, analyze, look at some graphs, look at some metrics, and then decide, okay, this is what the consumers want. This is what looks like people are lacking. So you implement this feature, and then like that, every week some new feature will be launched. So people were implementing these algorithms to solve the problems, but this was not scalable, because again, due to the huge amount of data that we are dealing with, how much of specific problems can be solved? So we wanted the computer itself to learn uh, what is that data that is being served, and what is the solution that matches well with this data, with the input information. So we wanted the computer itself to figure out, and that gave birth to that field of data science and machine learning. This might have been covered in other sessions, but I thought it's good to give this preface here. Now, for the purpose of this particular session, I'm going to be very specific and having a very narrow focus, because this is a small session of up to 1.5 hours, right? So how much can we cover? It's a huge field by itself. So it's going to be a very narrow focus. And the intention is to optimize the time for learning some core concepts of data science and machine learning by looking at code snippets. And I'll not be dwelling into too much depth on things as well, because for the same reason. And why are we doing this? Because as engineers, academics, when you face situations, when you talk with people who are dealing with implementing data science or machine learning, you should be able to identify these concepts. You should be able to have an idea of what they are doing. I think that's what I'm intending to accomplish through this session. I'll also mention what's not in scope in this session. So I'm not going to cover the Python programming language itself, because that itself is a big thing. I'm assuming that some basics of any programming that you are familiar with. I will also try to explain what is happening when I go through the code snippets, so that even if you have a very, very basic understanding of some programming language, you will be able to understand. And by the way, Python is a very very readable, very user-friendly language. So it should be simple for you to get what's happening. Um, and I'm also there to explain things. So yeah, and I'm also not going to cover machine learning environment, because just setting up the environment so that we could apply data science and machine learning concepts itself it can be a separate session. So I'm not going to cover it online. You can search for the information online to set up your environment. I've provided some links at the end of the slideshow to give you some pointers there. And also, I'm not going to talk about scaling, where we are dealing with huge amount of data. That's not within the purview of this talk. Okay. Let me talk about the basic steps involved in doing a machine learning implementation, irrespective of whatever language that we are using. There could be different ways you could do that, not just in Python, not just in using a particular technology, but these are essential steps in any machine learning implementation. The first step is importing data. As I said, data is what has given birth to data science and machine learning, first of all. So we have to get access. We have to have access to good quality data, and we should be able to import the data, download the data to your system. So that is importing data. And second step is cleaning up of the data. Typically, if you think of a database has could have like 10-15 different columns. That particular table can have 10-15 different columns, and potentially thousands or millions of rows. And when we talk about machine learning, will we will always be interested in only certain specific data for training the computer to solve a problem for us. We will go into some example as we go through the slides. And as I said, if you're talking about only few columns, what we'll do is like we'll only filter those columns for all the rows, and we'll ignore all other information. That is one of the way we clean the data, and by filtering the data, filtering only that information that we are interested in. And second thing is you could also be transforming the information in the data. For example, let me talk about I'll talk about the example later, and we'll go into the details. It could be like you are having particular data information in, let's say, dollars. You could be converting that to rupees because you are dealing with you're solving problems for Indian customers. So you could be converting the dollar information in a column to rupees. That's an example, right? Or you could be combining multiple different columns and deriving a third column, so that new information will be useful for your machine learning. The third step is splitting data into training set and test set. This is a very interesting way in which machine learning is very different from typical way computer science problems are solved. This is where it starts to get interesting, because what happens is, if you have ever solved any computer science problem, it could be a very simple problem, very simple program that you have written in C or C++ or Java. What you will do is like you will have a problem in mind. It could be, for example, finding out if a given number is prime number or not. And for that, you will have input as a number given, and your program will take that input, and then it will have certain procedures to process that number. And then at the end of that program, we will know if that particular, ideally, if your implementation is correct, it will tell if that number is prime or not. And this is the way typically any problem solving have always happened for all these decades. But with machine learning, what we are trying to do is, given data, like for example, prime numbers, talking about the same example, let's say we have 100 prime numbers, and we also have, let's say, 100 non-prime numbers which are not prime. This will be the input data, total input data, and each of the datum here has the number, which could be either prime or not, and the second value is that boolean, let's say, which indicates whether it's prime or not. So it's a tuple with two information, a number and answer that whether it's prime or not. And we have 100 plus 100, 200 numbers like that. Now this is the total input information that we'll have. Now what we will do is give this information or part of this information to the computer, and the computer has to decide, based on this information, any new prime number or number that you give, it will have to decide whether it's prime or not. So in a way, we as humans are not doing
Vijay,
that. Yeah.
sorry for the interruption. Have you changed your screen, Vijay? It's still visible for us as basic steps in machine learning implementation.
Yes, ma'am. I'm just giving a introduction example.
Okay.
I have another example where I'll
That's
get
fine.
into the depth of.
People started commenting that whether the screen is changed, we are not able to see it. That's the reason, Vijay. Nothing else.
Sure. Thanks, ma'am.
Oh, you can proceed. Thank you.
Yes. So this is a very initial example. Don't worry if you are not clear. I'll go into a more in-depth example like in few minutes. So what we are trying to do is like we are giving an input to the computer, and the computer will come up with the algorithm in the machine learning methodology. And based on that algorithm which that computer has come up with, any future input, the computer will be able to decide whether it's prime or not. Now, that's a very simple example of how machine learning technique is different from any other way you might have solved problems by writing programs. Okay, so this information is needed for me to even explain that, what is training set and test set. Training set is the set of data which is fed to the computer. In this case, it's called a model. And test set is the data with which we will test our model. How accurate is the computer figuring out whether it's prime or not in that example that I gave. The fourth step is creating a model. We will come up with a model of how the computer will use the training set. And the fifth step is testing the output. Testing the output is basically trying to see how our model is performing, where we'll also measure the output, how accurate it is. And sixth step is to improve, because after testing the output, we will know how well the computer is doing, how well the model is doing, and we will improve on that using multiple different methods, right? Cool. Okay. Now I'll go into a specific problem. Okay. Um, iris flowers. Now, iris flowers are beautiful flowers. There are many different varieties of it, like I think 300 different varieties. But for the purpose of this problem, we look at 3 varieties. You can see that even though they look similar, they are also a bit different, even in the picture. And there are different types of iris flowers. And we are going to come up with a machine learning technique to differentiate these flowers, given an input to differentiate these flowers. Okay. Now, the data set is not going to be images. We are not going to solve a image recognition problem. We assume that the image is converted into certain data points, like what you can see here. You can see an array where we have 5.1, 3.5, 1.4, and 0.2, and similarly different values. So this is the data array, and then there is a target array which has values 0, 1, or 2. I assume again that people are familiar with the concept of an array. Array is nothing but a list of values stored in as a data structure in computers, right? And target names is what are these numbers? 0 is Setosa, versicolor is 1, and Virginica is 2. So this is our input data set, which has all these arrays. And what are these 5.1, 3.5, 1.4, and 0.2? These are different parameters which explain these different flowers. And in this particular case, in case of this data set, they refer to the petals and sepals, width and height. Now, petals and sepals are biological terms to describe a flower, and we don't have to get into those details. But you can assume that these are descriptions which describe individual flowers. Let's say we have collected some 100 flowers from our garden. These are descriptions of each of those 100 flowers, and those 100 flowers can either be of type any of these 3 types, right? Yeah. And when you look at above, you can see that how we are loading this data. This is a sample data of flowers, and we are using that sample data to show how machine learning works. Okay. So this sklearn is a library which helps us get access to different data sets. So you can think of it as a toolkit from which we get access to different data sets. We are importing this iris data set. Iris is the flower, and we are loading that here to a variable called iris. And this iris looks like this. It has, let's say, 100 different flowers description and what those flowers are, one of these 3. Now, what I just described is importing the data. We have just done import of data. from this particular library. All right. Any questions? I want to take maybe a minute or two. Any questions? Something basic if I'm communicating properly.
Participant, do you have any questions? You can interact. But thing is that Vijay, there are a lot of participants actually. Even they can paste it in comment also. If you keep interacting, no, you will not be able to wind up. That's the thing. There's more than 100 participants now active. If there is serious, let them just commentate at the end of the session. We'll have an interaction.
Yes, agree, ma'am. That works. Yes. So I will check the comment once in a while, and then I'll answer them. Yes, sklearn is actually it's a library which has multiple different modules, to be specific. Data type U10. Is there something in the? That's the data type of that particular array. So we don't have to get into that specifics. It could be the particular type of that data which is supported in that library. So we don't have to get into that. So, but what's important is once we load the data, this is how the data looks. There is a data key which has the list of all flowers with different descriptions of its petal and sepals and its height and width. And then we have another key called target, which has the information whether each of this, when let's say if you look at 0, right? 0 means it's setosa. The first array item with 5.1, 3.5, 1.4, and 0.2 is a setosa. And the second one is also a setosa. Like that, a particular array element is 1, it will be versicolor. So we are just this is just a data which says if the petal is of length and this length and this width, and the sepal is of this length and this width, it is versicolor, it is setosa, like that. So we have just loaded this information, right? Yeah, so now we have imported the data. Now cleaning the data. Now cleaning the data, we're not going to clean the data here because we are importing the data from a very standard library, the sci-fi kit library, sklearn in this case library. So it's already very much cleaned, and we can trust the source of the data, and we don't have to transform anything also, because in this case we'll need all the attributes. So there is no cleaning of data. We go to the next step. Okay. Now we have loaded the iris information into this iris variable. Now we have to. Now what we'll do is, like, we already saw the data and the target element, right, within that iris. We are taking that out and putting that into separate variables, x and y in this case. So the data is put into x, and target, which is the response of what flower it is put into y. All right. And we are also getting few other information from the iris data, which is feature names and target names. Now, what are feature names and target names? I have just printed it here. Feature names are nothing but what I described: the sepal length, the sepal width, the petal length, and petal width. Sepals and petals are different parts of a flower. Now, target names are these different flowers, different types of flowers: setosa, versicolor, and virginica. So that's what target names are. So this is just a description and continuation of loading the data set. Let's talk about splitting the data. We come to this interesting part now. Now, there's sklearn also has another module called model selection. Now, within this model selection module, we have a function called train test split. Now, what this function does is what I described some time back. Given a input data set, it will help us split the data into two sets, a training set and a test set. We will be training the model that we build with the training set, so that the computer will figure out, oh, okay, the sepals are like this, the petals are like this. In this case, the data says it's a particular flower, and it will look through all this, let's say 60, 70 different entries, and then it will find out something. Okay, in some way it's a pattern recognition, you can say, but it's building a model in proper terms. And a test set is where once the model is built, we will give that test set information, some of these flowers for which we already know. We'll give the test set and then check how good is our model. So this method, train, test, split, takes this x and y variable, which are the data and the target, which contains all the data and all the target. Target is what flower it is. And then it also takes a variable attribute. It's called test size. I'll come to that again. And in response, it gives it returns 4 items in its response, which is x train, x test, y train, and y test. What are these? Now, x train is nothing but the training set. X is split into two parts, the training and the test. This is input. X is input, if you remember, right? X is the input data. So the training part of the input data is x train, and the test part of the input data is x test. Again, y, which is the target flower names. The training part of the flower data is y train, and the test part of the flower data is y test. So this function basically splits the data that you give, that these two variables you give, into 4 parts. That's what this function does. It's already implemented in a library. We don't have to do the splitting. If you have to manually do all the splitting based on different criteria, for example, in some case, if you give an let's say there are 150 items that we have. Okay, in this case we are splitting them into 120 and 30. For training, we will use 120 flowers. For testing, we will use 30 flowers. Now, that's one way to test. We may decide after some time to split the data into 150 because we feel we need more data to test, possibly, perhaps, right? So it could be possible. So we may have to split it differently. So if you implement the splitting, it can be like a big program by itself, which has to take into consideration different ways that you may want to split, different data types that you may take. Now, all that is already implemented and available for us in that scikit module, model selection, and this function, specific function, train, test, split. Now we have all this information. We can here you can see that I've printed the X train shape. Shape here refers to think of it as a two-dimensional array. Okay, array which has 120 entries, each with 4 columns. Think of it as a table, right, with 120 rows and 4 columns. And the X test table has 30 rows and 4 columns. The 4 columns, we know what they are. We were discussing that, the petal, sepal, width, and heights. Now we have split the data into training set and test set, right? Any questions? Yeah, Tina has asked, 0.2 means 20% of data. That's correct in this case. 0.2 means 20% of the data, because we are using 20% of the data for test. The function is actually splitting 20% of the data, in this case 30 entries, into X test, as you can see. Okay, I'll continue. modeling the data using classifier. Now, there are different machine learning algorithms, and classifier is one of the classic machine learning algorithms that that typically companies use. And even if you are building some interesting product, you will be noticing that you are using classifiers. And we will be using a classifier algorithm for this purpose of this problem that we are looking at. And we will be using a particular type of classifier called k-neighbors classifier. You can read about this k-neighbors classifier. I have also put a link to a page which describes this algorithm, k-neighbors classifier. But it's good to get information on what it is, how it works. But for the purpose of this session, you just need to understand that k-neighbors classifier is an algorithm which, given a set of data, it classifies the data into different sets. That's all we have to know at this point. And we have a particular module called neighbors in sklearn. So from sklearn.neighbors, which is the module, we are importing this particular algorithm, importing k-neighbors classifiers. And in the second line, you can see we are actually initiating a variable with this algorithm with a parameter called n neighbors. Now, n neighbors is a parameter which is needed for this algorithm. Again, we don't have to go into the specifics. To just describe in brief, neighbors is a way this algorithm decides to split the data, decides to understand the data, you can say. Now, this is stored in a variable called knn, and in the next line, you see we are calling a function knn.fit, and then we pass the two variables which we discussed before, xtrain and ytrain. We are passing these two variables, xtrain and ytrain, to this function called fit. Now, what are we doing here? Now, k-neighbors classifier is a algorithm which is one of the famous algorithms which people use, and we are importing that from a library that already exists. Now, we don't have to implement anything about that algorithm. It could be a very complex algorithm, it could be a very simple algorithm. We don't care, because already somebody has very dexterously figured out what is this algorithm. They have also implemented this algorithm, they have tested this algorithm, and now it's part of a standard library. So you can put all your trust that whatever that algorithm is, it's implemented properly, and not care about reading about that algorithm, understanding it, implementing it, testing it, and all that. We just import it and then we just use it. But when we use it as an algorithm, you might have to instantiate certain algorithms with some parameter. And for that, you might have to do some reading. Here, we are just passing that parameter as n neighbors 3, and we are assigning that to a variable. Now, this variable knn is still an abstract algorithm. It doesn't know about the data which we were dealing with in the last few slides. Remember, in the last few slides, we actually imported the data from a particular library regarding iris flowers. And then we have also went into checking what this particular data is, what is the different attributes that are there, what are those flowers. I also gave you a description of what are these, and then we also split the data. Now, the algorithm doesn't know all of this. We only know it. It's all part of our code. Now, we are just passing part of that data which we have split, which is xtrain and ytrain, the training input and the training output data, to this algorithm instance, knn. Now, this is to train this. Here we are this step is called training the model. we are modeling with this input data. So knn.fit xtrain and ytrain means we are training our model with this input data. There are some questions. Let me look at that. Vinod has asked if I want to do data cleaning manually, what are the manners I have to follow? Okay, so that's a very good question because I'm not covering that within the scope of this task. So one example that I talked about is, let's say we have a table of 1 million rows and 10 columns. And for solving the problem, you are, let's say, interested in only 5 of those columns. Now you can extract only 5 of those columns from that table or data set that we have and ignore all the 5 of that other columns. Now this is totally possible using what's called pandas library in Python. I'll just type it out. Pandas library is a data analysis library for Python. So it has very good support for dealing with data input, data transformation, and data analysis. So you can search about that, read the documentation, and then you will get to know how you can deal with data, create new columns, for example, using existing data, etc. And okay, I'm going a little bit further above as well. Jamie has asked how to data split for validation. I think I've answered that, right? We actually use the inbuilt function, which is already available in the scikit, the train test split method that I talked about. That's how we split the data. What does that x train dot shape represent? Yeah, as I said, it represents the shape of that data, the number of rows and number of columns. Okay. Yeah, I think Bala Kodandaraman has answered it. Tirumurti has asked, can you give us the link for k neighbors classifiers? I'll give it at the end of the session. You can also search it online. You should be able to find many links. Okay, and Tina has asked, how is the value of n fixed? Does it depend on data size? Let me look at it. I'm not sure which slide she's referring to. Let me try to answer that with some assumption. In this particular example that we are looking at, right, we are just looking at a small set of data which has just 150 rows, which is just to show how machine learning works, right, in Python. Now, if we look at big companies like Google or Amazon, they will have like petabytes of data, like thousands of gigabytes of data, right? Now, they don't have any problem with the with availability of data. What they have problem though is what subset of data they have to take, and that they come up with experimentation. They figure out a particular value of n. They will decide, let's say, to take 1,000,000 rows, and then they figure out, okay, this is too much information. It's a lot of garbage data that's coming in. They might reduce the number of data that they take, or they might increase depending on the use case. And another interesting problem that we'll have to deal with when we are talking about splitting the data into training and test is, what is the percentage of the data that will be split? It could be 20%, it could be 50%, it could be just 10%. Again, that depends on the problem at hand and what sort of use case we are trying to solve, and how much how much better we want our algorithm to be. For training our algorithm, we need a good variety of input data so that the model, the machine learning model that we are coming up with, knows the different varieties and comes up with a good model output. But at the same time, to test that model output, you need a good variety of test data as well. So it's a it's some sort of a compromise that you have to make. It's a trade-off, right? Mm. Okay. Somebody has asked, why have we taken n neighbors is 3? Um, it's just a default value which people typically use. And also in this particular problem, we are having 3 different types of flowers. So maybe 3 is something that will make sense, is what I thought based on my reading of that algorithm. But let's not get into that specific. Otherwise, the entire session will be talking about that algorithm. Yeah. Number of clusters. It's not necessarily number of clusters in my understanding. It's if you read the documentation of this algorithm, they will talk about what are these. What does n neighbors stand for? It's about the number of neighbors which the flower should have, which should be of the same type uh, within the implementation of the algorithm. So okay, let me continue. Okay, so now we have just built the model, the machine learning model here using the k neighbors classifier algorithm, and then we have also fed the input data, the training data, the X train and the Y train, the training input and training output data specifically to the algorithm. Okay, now we have created a model and ingested the input data into the model. Now we have a model which is ready for us to test, right? Excuse me. So so what we can do now is, in this model we can make predictions, because the computer is now ready. It has created it has solved the problems by itself, you can assume, and then but not 100%. It may be right or wrong, because it's again a machine learning. Machine is learning with the data. Now to test the model, we can use the predict function here. You can see make prediction. So we use knn.predict, and then we pass the test input. If you remember, right, we split the data into 4 parts. There is a X train, which is the training input, Y train, which is the training output. When I say training output, I'm talking about the name of the flower. And then X test, which is the testing input, and Y test, which is the testing output, that is testing flower name. So X test and Y test, we have not used it, right? So we are using that here. We are using X test, which is the testing part of the data, the 30 flowers here, which we have just built the model using the 120 flower information that we have. Now we are using these 30 rows, which have the dimensions as well as the output. We are testing that. We are basically now passing that input information and asking the algorithm to predict what flowers they are. Now, when we call this function, it gives an output, which is y_pred for prediction. And it has predicted. Now it has returned a response, which will be like a list of flowers, which the algorithm thinks they are. Now at this point, we have 2 informations. One is actually what those flowers are, which are there in Y test, and then what the algorithm has predicted those flowers are, which is Y pred, right? Now these 2 information we have, Y test and Y pred. Now we can use another module here called metrics. in sklearn there is a module named metrics. So from sklearn we are importing metrics, and metrics has method to calculate the accuracy score. You pass the actual response along with the response that the model has predicted. You pass both of it, y_test and y_pred in this case. When we pass both of it, it will calculate what is the accuracy. Now we have called this function and we have printed it so that we can see, and you can see that the prediction accuracy score is 0.93333, which out of 1 is the perfect score. So this means 93% of the time the model is able to accurately predict what flower it is, which is great, right? We just built a machine learning algorithm which, given an input data of some features of the flower, it's able to predict 93% with 93% accuracy what flower it is, which is really great. We made the computer learn by itself what are the flowers based on input data. Awesome. Okay, I'm looking at some questions because it's important for you to get. This is probably the most important slide that you have to get. Tirumurthy has asked how y_test and y_predict are different. Okay. I think I explained that. He has asked it a couple of minutes back. I'll explain it again. Now, x_test is the, sorry, he asked what is the difference between y_test and y_predict. Okay. Now, y_test is one of the output which you got when we split the data, right? So we would split the data into four parts in this case, and x train is the training input data, and x test is the testing input data, y train is the training output data, and y test is the testing output data. I might have I could have renamed it maybe in a better way in retrospect, but basically x train and x test has all the flower information for training and test, and y train and y test has the result of what flower it is among those three flowers that we talked about. What flower it is, that output is there in y train and y test, the actual output. Now for that 30 entries that are there in the test data in x test and y test, those 30 flowers input, including the petal and sepal information, is there in x test. That output of what flower it is there, it is actually is there in y test. So that's what is the y test that we are using, the actual output of what flower it is. When we call the knn.predict with the input test data, which is x test, now the model is predicting what flower it is. Now that's the prediction. That's y_prediction. Now I hope I answered the question of what is the difference between x test and y test and y pred. What are the other metrics which can be used to evaluate the classification model, sir, apart from accuracy? So accuracy is a very important metric that people measure. Precision is another metric which people use. You can read about that. It's yeah, somebody has also answered. There is a F1 measure, which is also another score. So there are many different metrics that we can use. Okay. Okay. Now we have used the test data, and we have also measured the accuracy of the model, right, which is 93%. Now, all right. Now we have a model which predicts what is a flower given the sepal and petal information with 93% accuracy. How do we use this model? I've given a sample here of how we can use this model. Now we have a we have a variable here called knn, right? I've just renamed that to model here. What you see as model here is nothing but that knn. I am creating sample data with different values for sepal, petal, width, and height. Just 2 flowers, right? And I am calling the model's predict function with that sample data, just passing that array of arrays to that sample data, and it's returning the predictions as a array again. And what I'm doing here is don't get into the complications. It's a very Python way of just getting the names of that flowers from this prediction. And then here I am just printing that names. So these 2 flowers input data is being predicted as versicolor and virginica, which are the one of the 2 types, 2 among the 3 types that we discussed. So given some few numbers, the prediction model is able to understand them as the specific parameters which we talked about, and it's able to predict some information. Now this is just random, not really random, but similar numbers as I saw in that input data. I've just given that input data, and the model is able to actually understand them and predict the flower types, which is cool, right? Now as you might have observed, this is different from the test data. The test data is actually true data. We know that those 30 rows, we actually know what those flower types are. But here we are providing, we are calling the input. We are calling the machine learning model with input information for which we don't know the answer, and the model is giving us the answer. And at this point, we can confidently say that with 93% probability that this prediction is true, because we have also measured the accuracy, how accurate the model is. So we can reasonably say, these are the flower types given these dimensions, and this is 93% accurate. Okay. Suppose, let's say the accuracy is too low, let's say 0.42. Now what should be done to increase the accuracy? Okay, we'll get to that, Lakshmi. Okay, now this is just to sort of kindle your curiosity. I've just created a couple of visualizations using this data. We are not going to explore how to create these visualizations. It's out of scope of this talk. But what I've used here is I've used the same iris data that we have imported, and I'm just plotting that input data, plotting that whatever data that we imported into graph, so that that gives you an idea of how this input data, the data that we have used, which we imported from that library, looks. For that plotting, I've also used a matplot library, which is one of the famous libraries for visualization, and I've fed this data that we imported in specific ways. On the left side, you can see that there is a graph which has sepal length and sepal width. Sepal again is one of the biological terms of describing parts, the sepal in a flower, and it's basically plotted the 3 different flowers in different colors, with the x-axis as the sepal length and y-axis as sepal width. And looking at the graph, you can see with a human eye, you should be able to see there are some similarities. For example, for setosa.
Able to see the graph.
You're not able to see the chart?
Yes, sir. So using our predictions.
It is visible. I think you have a network issue, please. Vijay, continue, Vijay, please.
Okay, ma'am.
Somebody has a network issues, they are unable to see.
Sure.
They'll get it later. That's it. Thank you.
Yeah. So you can see that the setosa, which is a bit purple in color, has lesser sepal length and it has more sepal width, right? And and if you look at versicolor, which is a little bit blue-green in color, it has almost lesser sepal length as well as lesser sepal width. And virginica has typically has bit greater sepal length and lesser sepal width, right? Now, the reason I'm showing this is the whatever that the model that we have built up and the input data that we have given to the model, it's not like some magic that the computer is doing. This model is built up to use the input data and classify the input data based on the numbers, the way these numbers are related to each other, the ratio, etc., and accordingly with certain confidence classify them as one of these, right? So with a human eye, after observing this particular graph, you should be able to, with some probability, classify a given flower with this input graph that you have seen, right? So the computer is essentially doing the same thing, but somebody has already written a very generic tested algorithm which does it for us. And what we have seen is a way to use that algorithm to just apply the input data to do what we did. If you look at the right graph, it's again similarly for petal length and petal width, and we can even see a more clearer, um, I would say, relationship where setosa petal length and width is so small, and the other two are a little bit bigger. In this case, virginica is even has a bigger petal width and petal length. So this is being recognized just using the data. The computer learned this. We need
இந்த வீக் ஃபுல்லாக மெக்கட்ரானிக்ஸ் லேப் இல்லை எனக்கு FTDP ப்ரோக்ராம் இருக்குது ஃபேக்கல்டி டெவலப்மெண்ட் ப்ரோக்ராம் அட்டன்
Sorry,
பண்ணி ஐ ஹேவ் ஃபேக்கல்டி
some
டெவலப்மெண்ட் ப்ரோக்ராம்
participant please muted, please.
இஃப் யூ கம்ப்ளீட்னா யூ கேன் கோ.
Okay. Vijay, you unmute yourself. Vijay, I muted everyone. You unmute yourself.
Yes, ma'am. I've unmuted myself. Thank you.
Yeah, please, Vijay, please. Sorry for the interruption.
Yeah, no problem, ma'am. It happens sometimes. It happens in even
please,
our team meetings sometimes.
Okay, Vijay. Thank you.
Yeah, so you can see that we as humans we have to actually see this particular graph, which is again generated by a computer library, to recognize, okay, now these flowers are small, these flowers are a little bit medium, these flowers are bigger, but the computer model, machine learning model, has learned it by itself. So that's the beauty of what we actually did. And this is just a chart which I thought I'll plot to show that. Yes. Now I have some references and resources that I'm sharing, but before that I'd like to take any questions that you might have. I can talk about it. Anything general or anything specific to the example that we talked about.
Vijay, just one question. Are we using any predefined libraries in companies like Google and Amazon, or you're writing your own algorithms?
Yeah, I think it's Arun Karthik. Thanks, Arun Karthik. Yeah, it's a good question. So there are a lot of these pre-existing libraries which are also already there because it was developed by some company. Now, Facebook could have developed something, Google could have developed something, there may be some research organization at some university might have developed something. So a lot of these libraries were developed as a result of people observing, okay, this is a very generic problem, so many people need it, so let's develop a library. And at certain in certain occasions, these algorithms are directly useful, directly relevant, and it will be used. As you might have observed, many of these algorithms models that we talked about, they take in a parameter. Here in this case, it takes n neighbor parameter. So the version of algorithm is customizable based on certain attributes, and these attributes typically provide that flexibility to be able to um, apply the algorithm in a specific way for that model, which is optimized for that use case. So that is one. Second part is, of course, the companies as well will have their own proprietary algorithms which they have developed for their particular use case or business problem that they are solving, which could as well be an extension of existing algorithms, um, which they might have figured out that it doesn't solve our problem in the best possible way, so we'll have to extend it in certain ways. Those extensions may be only within the company, and they need not have been made public in any package or library.
Thank you, Vijay. Thank you.
Okay. Somebody has asked, is there any association between accuracy and training and test ratio? Yes, I will come to that. I actually missed covering that point. I'll come to that. Or on how relevant the test ratio is and what it is useful for. How to increase the accuracy if it's too low, Lakshmi has asked. I'll also again answer that in the same way. Is there again? Okay, same question. Okay, so we talked about different steps, remember, in the beginning. So we need to import the data, we need to clean the data, then we didn't exactly clean the data, but I gave an example of how to clean a data if there is a need. And then we split the data into training set and a test set, which we did using the train split function. And then we created a model. We used existing algorithm that's already there with a specific parameter. We created a model instance, and then we fed the model part of the training set to what we typically call train the model. That step where this is a step where we actually used an existing algorithm from the sklearn neighbors module. We used the algorithm. We passed a particular attribute here, and then we call the fit function with the training data. Now this process is called training the model. We created the model, and then step 5, test the output. We also tested the output by passing the test information to the model, and then measuring the accuracy. And then the 6th part is improve. Now there are different ways we could improve this particular model, the machine learning model which we have trained. Where is this? Okay, I'll talk about few ways that we can do that. One is we can have more test data. Here, since it's anyway an exercise, we had only 150 rows, and we were using that data. If you have more data, let's say you have 1 lakh rows, the algorithm will be able to much more precisely say what flower it is, because it will have a lot of variety, and it will be able to use all that input data to train itself to be better. It's a excuse me, it's very similar to how humans also, as you see, you might have gone to this tender coconut shop. The person who's there will be able to easily identify which of that coconut will be having water, or will be having thick coconut flesh. He will be able to easily say just by looking at it or weighing it, right? Here you can think that even the computer is also doing that. It's taking up certain attributes of the input, and then it's able to make a prediction. Okay, this is probably this, right? Now the more the flower data that we pass, the model will be trained better to answer our output. Now that is one way we can improve. The second way is the test size, which is 0.2 in this case. The testing, we are only using 20% of the data for testing. We could play around with that. We could change the testing size to be let's say 40%. Instead of 20%, it can be 40%, so that we would be able to see that for 40% of the data we'll be able to test. But it's a trade-off. Then in that case, you will mean 60%, only 60% of the data will be used for training. So typically it's a trade-off, and what companies do is, like, anyway, the data that they use is a sample data. Let's say they may have 1 billion entries. So they will take a sample of, let's say, 1 million, and within that 1 million, they will split it into training and set. And they will figure out as they go what will be the test ratio that works. So this is something that you can play around with and see if your accuracy improves. And another way you can improve is, you can try to see if you can use different algorithms. There are usually, depending on the problem, there are different type of other algorithms you can use. For this particular problem, we could have also used a decision tree classifier. You can see in the comment here, the slide, the decision tree classifier. Here, we can just instantiate that algorithm to create our model, and then we can train the data in a similar way, and that will give you a different output compared to this particular algorithm. So you could try some 2 or 3 different algorithms and see which one works well. And typically, if you are a data scientist, this is usually a job of a data scientist. They will look at, what is the problem, what is the input information that we have, what different algorithms can be applied, and what are all the attributes that we can pass to the algorithm that is optimal, and then decide on which algorithm and which parameters we should pass. So these are all the job of a data scientist in an organization. So we could change the algorithm and see if that improves our score. So this is something we can do. Is there anything else that we can do? I think I've covered most of the different things that you can do. We can also see, in this case, we have the sepal length, sepal width, and petal length and petal width. These are the different attributes of a flower that we have. We can also explore that, is there any other attribute of the plant that we can use if we have access to that information. For example, it could be, let's say, the plant's height, the height of that plant. Maybe it's different for these different flowers. Maybe I'm just assuming here. If it's different, maybe we can use that attribute as well in the training data. Maybe that will improve the accuracy of the data. Right. How to compare different algorithms and their accuracy? That's pretty easy. You will have to basically change the algorithm, run the program for that input, and see how much is the precision, and then precision and accuracy, and then you also test with that other algorithm and see how different the accuracy values are. How to define and import our own data set? Anything in the form of a CSV? Yes, typically it will be in the form of a CSV. And existing data sets will also be in the form of CSV, whatever that you download. Kaggle is one of the sites. Kaggle, Kaggle, Kaggle is one of the sites where you can go and check out a lot of different data sets, existing data sets. There are a lot of other sources as well you could find. Okay, as I'm putting the following questions to you. Most of the data science and machine learning courses in web comes with using existing libraries such as scikit, not including the algorithm development. Yeah. Okay. A data scientist, ML engineer's job is to only analyze the data using existing libraries, or is it required to know how to develop algorithms? It depends. But I think definitely a basic level, any data scientist should be able to know, understand the problem. They should be able to do their research to know all the different types of algorithms that exist. They should be able to map the problem to the algorithm. They should be able to know how to use the algorithm, use the model for training the data, how to split the training and the test data, what are all the attributes to use. These are typically what data scientists do along with working with ML engineers. how to develop algorithms, that's typically advanced. There may be advanced data scientists who actually work on those algorithms to develop new algorithms, but most of the people will not be doing that. What engineering knowledge is required for any data scientist or any machine learning expert? Engineering knowledge. People, I think definitely data science and machine learning are advanced computer science field, which is also recent, and they have built on top of existing computer science fields like like uh, uh, like algorithms, data structures, databases, big data. So it is built on top of all these existing fields. So it will definitely be an advantage if you are from computer science or IT background. But as long as you have an understanding of how to build products, how to solve problems, even if you are from other fields, you should be able to learn data science and machine learning concepts. And working, if you join some company in these areas and develop that expertise, you could become an expert irrespective of what studies you might have done. Do companies differentiate machine learning engineers and data scientists? Not all companies. I think the bigger the company gets, typically they differentiate data scientists and machine learning engineers to do different aspects of the work. Data scientists will be looking at the algorithms and how to optimize the algorithm. Machine learning engineers will do the whole process that we talked about, uh, from the data, identifying the data, cleaning up the data, and integrating, building the pipeline to pass the data to that module, which builds that model, taking the model output and putting that in use in the production system. So they will do everything that's around that uh, to make use of that model. What all the essential skills required to become a data scientist? Tools and mathematical engineering skills. For a data scientist, I think he should typically be pretty strong in mathematics and statistics, and it's useful, of course, to also understand computer science, and um and for both machine learning and data scientists, they will have to understand certain technologies, Python or certain other languages for data analysis, data analytics, or machine learning. There are few new languages which have also come up. They can be experts in that. That will be useful. And then understanding these libraries, tools. Yeah, there are few tools. There's something called Jupyter Notebook, which I've actually used when I built this presentation. So Jupyter Notebook is something that they should be familiar with and knowing how to use. Anaconda is a environment which already has a lot of machine learning libraries built in, uh, which will come handy when if you are a data scientist or a machine learning engineer. Is it required to have a PhD in data science to become data scientist? I don't think so. In companies, have a lot of scope for data science and machine learning. Then they don't have enough people who have a master's or a research experience in data science and machine learning. So what they do is like they find out folks who actually have experience, market experience in machine learning or data science, and they make use of them, or they train their existing engineers to go through some course and uh, start start practically using their knowledge and skills in the business and the product development. So that's how companies are building their own data scientists and ML experts in some sense. So it's not required to have PhD in data science, but of course it will help if you have a PhD. You can you'll definitely be sought after. But even if you have a master's degree, or if you have done some projects as part of your even bachelor's degree, if you've done a couple of projects and you have some expertise, you could be in demand if you're able to present yourself and the work that you've done. Okay, thanks a lot for aggregating all those questions, Arun. Somebody has shared, Prasanna has shared a government website for public data sets. That's very useful for people. Thanks, Prasanna. Thanks, Arun. I also had a lot of pleasure in sharing all these things. Okay, somebody has said hyperparameter usage in ML. I'm not aware of that, Silva. Shall I modify the data of wrongly classified to get more accuracy? Ramesh has said. Is that question that the input data is wrong? Some parts of the input data is wrong, and can you change it to get better accuracy? I think you can do that if you are the owner of the input data. As in, you could of course download the data and change it, but if you're wrongly changing it, the implication is that it will actually do the reverse. It may result in lesser accuracy or lesser precision. So yeah, you are responsible for your actions. Okay, so that's it. I'm just sharing some few references and resources.